Let's now continue with the development of this module. So far we had built this small module that is composed of these two rigid bodies that are connected through a hinge connector that is positioned here. Okay, so let's remember that, let me go back here to ANSA. So here I have my module, and well, before I continue, I forgot to show how to save this module in ANSA in the last video. So to do this, you should simply click on File and Save As or Save, and then you can give this file a name, and the extension of this file is .ansa. Okay, so I already saved it as excavator.ansa. And now if you want to open this file, so let's suppose that we have here, I'm going to click File, New, Discard. So I have here an ANSA with nothing opened, and then if I want to open this module, I should simply go to File, Open, Discard, and then select the .ansa file that you had saved, and then here we have it. Okay, another important thing to do when you open this up is to change the deck to Abaqus. To do this, you should click here on this button and hold until you see these options, and then you should select Abaqus deck. Okay. All right. So in the last video, then we had. Let me deactivate the visualization of CAD by clicking here, and then so in the last video, let me maximize the element. You see that in rigid body we have two rigid bodies, arm 1 and arm 2, and they are connected by one connector. So we can double click on connector, and you see that there is this hinge connector that is connected that is connecting these two rigid bodies, and we do that by defining two tie node sets, and each one of these tie node sets is going to be part of one rigid body. So let's go back here to rigid body, double click on arm 1 for example, so you see that we have one tie node set here. And this node set is composed of one of the nodes that is part of that connector. And in arm 2, there is this other node set that has the other node of the connector. Okay, so that's how we connect two rigid bodies. It's important to understand that. And besides that, we have also defined one step. So if I maximize step, double click in step, and then you see that we have step 1 defined. We had configured this step. So we activated nonlinearity related to geometry, because in this module we are going to have large displacement, so it's important to have this as yes. This is one of the types of nonlinearities. We had also configured the time period, which is 100. This is a 0 time, which works like a percentage of load application. So 100 means 100%. And then 10 means that the time increment, the initial time increment means that we are going to start applying 10% of the load. Okay, so for example, in this step, I defined here in boundaries connector motion, this one. We had defined a connector motion for this connector. I'm going to double click on it to open the card. And then you see that we applied a displacement in the 4th degree of freedom, which means rotation about x, which is the axis that we define as the axis that we are going to have rotations for the hinge. That's the only degree of freedom that we can have rotations for this type of connector. And we applied a rotation of this amount, which is 30 degrees in radians. Okay, so this is just pi divided by 6. So 10% initial time increment means that we are going to start applying 10% of this rotational displacement. Okay? And then if the software thinks it's easy to converge, it's going to maybe increase to 15% for the next increment, and so on. Okay, so that's what we did in the last video. Now let's continue building this model. Let's continue creating other rigid bodies. Now I'm going to try to be a little faster because now you know how to do this. So let's be a little faster. We have an interesting mechanism here. And well, I'm not going to try to explain in details how it works, because I guess it's going to be easier to do it and then run an analysis to see if it's working. And then you're going to understand how this mechanism works by looking at the animation of the result of this simulation. Okay, so let's do this. One rigid body that we should have here is one that is composed of these two parts. Okay, so let's use this tool to isolate, and the selection filter should be PID. Okay, so we are going to select parts that has the same PID. You see that just 1 minute, let me close here this window because it's windy. And okay, so you see that the visualization filter is as PID, so that's why you see each part in one different color, which means that each part has a different PID. Okay, so the software automatically created a different PID for each part when it imported the CAD. Okay. Well, PID is just property. I know that this is confusing for people that are starting to use ANSA, but trust me, you're going to get used to it. You're going to understand more about it over time. Okay, so using this function and with the selection filter as PID, select this part, and you see that both parts were selected. I'm not going to get here any bolts or anything like that. Okay, I'm going to get the least parts I can, because as I mentioned, these elements that we create are just for visualization purposes. Okay, so now we are going to click here on this button, mesh, click and hold until you see these options, and then click in classic mesh. And then let's use the length function. And we are going to select by perimeters, which means, well, what are perimeters? Perimeters are these edges, these curves that are on the surfaces. And if we select here macros are the surfaces. Okay. We can select by macros or perimeters. The result is going to be the same. Let's select here, for example, by macros, select everything, middle mouse button to conclude. And then we can define here the length. It is currently 2. I'm going to increase it to 20 millimeters. Press on OK. And then you see that the distance between these pink points has changed, and it is now equal to approximately 20. This pink points is just, well, if we click here and if we deactivate perimeter grids, you see that we cannot see the pink points anymore, which means that these are perimeter grids, and this is what define the element size on the edges of the part. Okay. Besides that, we should also click here in mesh parameters, and then define the target length for mesh size as 20. Okay, if you closed your ANSA and if you opened your module another day, you should redefine it. Okay, unfortunately, you should redefine it. It didn't save with the module. Now click on OK. And we can now create a mesh, a surface mesh here for this part. Okay. And to do this, we should use one of these meshing algorithms that you see here. And since we are not interested in creating a good quality mesh, because these are going to be rigid bodies, we can use the free algorithm. And then click and hold until you see these options, and then select this first one. Select everything, middle mouse button. Now you see that the quality of the mesh is not good at all, but that's okay. And now the next step is to detach this mesh to the geometry, because right now if we try to hide the cat, we are going to hide the mesh as well. So to release the mesh from the cat, we are going to click here in volume mesh, and then there is this function release. Release shell or solid elements from the underlying geometry. Click on it, select everything, middle mouse button, and now if we deactivate the visualization of macros, you see that we can see the mesh. Now let's go to the Abaqus deck, and then we are going to use this function inside the elements group named utilities. Click and hold, and then keep holding. Go to change type to the entities, and now you can release the left mouse button. Now I want to transform it into R3D, which is rigid element, from shell, because right now we have shell elements. Select everything, middle mouse button, close this window, and now if we maximize in the database the element group, you see that double click in rigid body, we have one additional rigid body. Okay, double click on this rigid body, and then we can name this as connecting mechanism 1. Okay, I'm not going to give so specific names here. I'm just going to try to make it a little organized, but not so much. Okay, so you see that there is a reference node related to this rigid body, which is one node that is positioned, well, let me click here on OK. And you see that this reference node is this one that is positioned in the COG of these nodes that we had used to create this rigid body. This position was calculated automatically, and this reference node was created automatically when we used that function. Also, let me go back here to the rigid body card. You see that we have an element set related to this rigid body, which is an element set composed of all of these rigid elements, as we had learned in the previous video. Now click on OK. We should obviously define the tie node set for this one, but before we need to create a connector. Click on OK. Now let's show all. And you see that we have this additional rigid body created. Okay. Well, this rigid body, this one, activate the visualization of rigid body by clicking here, and then click here in pick, so that when we click on some rigid body, this is going to be selected here. So for example, I'm going to click on this one, and this is going to be selected here. If you want to deselect what is selected, you should click here on a blank space. Okay, so this rigid body should be connected to this one by using a hinge connector. Okay, well, I guess in the future we are going to have some issues using the hinge connector, and I'm going to explain later with more details why this issue is happening. And then we are going to transform these connectors into Cartesian cardon connectors. Okay, hopefully we have this issue, because then we can practice another type of connector. Now let's deselect all rigid bodies, and let's deactivate the visualization of rigid bodies, because I don't really like it. And to create this hinge, we're going to use the same strategy that we had used here. Okay, so I'm going to do this faster now. Firstly, let's go to topo module, click here, and then scroll down. I guess the camera is in front of it. Let me deactivate it. Yeah. We are going to create a point on COG, click and hold, and then release the mouse when you have it positioned on circle. Select 3 nodes that are part of this circle, and then middle mouse button, and then we have a point right in the center of the circle. Do the same thing on the other side. Remember that to rotate the view, you should hold the Control key and use the left mouse button. Now let's create a point on COG of points. Select this one, rotate the view, and select this one. Middle mouse button to conclude. Now we have one additional point in between these 2 points. Okay, let me deactivate, actually, let me activate the camera again. Now, the next step, well, let's deactivate the visualization of rigid elements. The next step is to create a coordinate system with the x-axis along this axis, which is the axis of the bolt that would be passing here. Go to Abaqus deck, and in the coordinate group, click in coordinate rectangular. Select this point to be the origin, and this point to define the direction of the z-axis. Middle mouse button, and then here we have the card that defines this coordinate system. Let's click on OK, and you see that the visualization of this coordinate system is too small, so we can change it by clicking in quality criteria, presentation parameters, scroll down, and then here draw sizes, coordinate system. Let's change it to 10, apply, OK. You see that the z-axis is along the axial direction of the bolt. We should change it, and for that we should rotate this coordinate system about the y-axis by -90 degrees. The direction of the positive sense of rotation is defined using the right hand rule, as I explained before. So in the database, let's look for coordinate, maximize, double click in orientation R, which are the rectangular coordinate systems defined. Well, a rectangular coordinate system is just a coordinate system that is composed of the x, y, and z axis, and that these axes are orthogonal to each other. That is, they are 90 degrees apart from each other. Okay, that's the basic definition of a rectangular coordinate system. So the one that we had created is this one. You see that when I select it, we can see it highlighted here. And double click on it. We are going to create a rotation about the y-axis, which is the axis 2 of -90. Click on OK. Now you see that the x-axis is along the direction that we want. Okay. Now we can create the connector by clicking here. Well, in the Abaqus deck, click here, well, inside the elements, because a connector is a type of element. You can see here in the database that a connector is inside the element group. So click and hold this button, and let's create a connector using 2 nodes. The first node is going to be this one. The second node is going to be this one. Middle mouse button to conclude. We should select a part in the module browser for this connector. We had created a part for it previously, but you see that we cannot see it so well. So one way we could solve it is to get here the module browser, click and drag it like this. Okay. Now we had created this part named connectors to use it to put all connectors that we create. Double click on it. And now we should select the PID for this hinge. We had created this PID before for the hinge that connects arm 1 to arm 2. We can't use it because this PID is defined using the other coordinate system. And now we need to create a PID that is going to use these other coordinate system. Okay, so we need to create a new one, right? Right click here and click on new. And then this is maybe ARM2, I'm not sure. ARM2, well, we can change the name later. ARM2 to connecting mechanism 1. This is going to be a hinge, so change here component 1 to hinge, and we should define the orientation of node 1, which is the first node that we selected, and this is going to be automatically the orientation of node 2. To define this orientation, select what is inside this field, use the question mark to open a list of options that we have, and then select this one that is the new coordinate system that we selected. Or you can select here in the viewport this one, and you see that the coordinate system with ID 2 is selected automatically. Double click on it, and then that's all we need to do. Click on OK, and then you see that we have this new property or connector section for this hinge that we can use. Okay, so remember that we have the visualization as PID, and we selected by PID. Well, a connector section is one example of a PID. Okay, there are many types of PIDs. PIDs are usually used to define the properties of some specific entities, not just for connectors, it's for all types of entities. Okay, so that's why I mentioned that you're going to get used to how ANSA works, and when you get used, you're going to see that this software is very powerful to create complex models. Okay, so double click on this PID that we had created, and then this is the card of the connector. This is the ID of this connector, the ID of the PID that we have just created. If we select it and press F2, we are going to go back to the card where we defined this PID. Click on OK. And here we have the ID of the first node that we selected, which is this node here, and the ID of the second node that we selected, which is this node here. Click on OK. And you see that we have the tool to create connectors yet activated. We can close it. And you see that we have the coordinate system, actually the connector created already. Okay. And we can see the coordinate system of each node in yellow. And you see that the axis 1, which is the x-axis, is in the right orientation. Okay, so this type of connector only allows rotation about x, which is what we want. It doesn't allow translation in the x, y, and z directions, and it doesn't allow rotation about the y and z axis. That's how a hinge connector works. It's pretty simple. Now we should define the tie node sets. Okay. Let's click here in show all, and let's activate the visualization of rigid by clicking here. And let me just check if this is the ARM2. Double click on rigid body, select ARM2. Yeah, this is ARM2. For ARM2, we had already created, double click on ARM2, and you see that we had already created this tie node set, right? With ID 4. So let's now modify it to include one additional node. So the ID is 4. Close this, and then click here, click on sets. And this is the set that has now only one node that is part of this hinge. And now we should include another node that is going to be part of this hinge, one of the two nodes. Now, deactivate the visualization of rigid. Right click on the set. Click on modify content. And let's maximize these like this. And you see that we have only one node selected, which is a node that is here in this hinge. Let me zoom out and zoom in this other hinge. And then now I'm going to select this node, for example. And then you see that now we have 2 nodes in this set. You should always manage how many nodes we have here, because sometimes when we are going to modify a set with no purpose, we can deselect the nodes that were already in this set, and then we are going to cause a big mistake. Okay, so now we have 2 nodes, which is what we should have. Middle mouse button, and then you see that we have 2 nodes in this set as expected. Okay, also notice that we have this new set that is composed of these rigid elements, and then we should change the name of this set because it's too large. And well, at least in the version of Abaqus that I have here, if I input in Abaqus sets with large names, it's going to generate an error and it's not going to solve the problem. So I'm going to close this, double click on rigid body, click on this one that we had just created, copy the name of this one, Control C, select the element set, F2, and then Control V here, paste the name, and then underline rigid elements. Okay, I know that this name is yet large, but well, for me at least, this is not going to yield to an error. I don't like to use spaces, even though there is not so many problems that occurs with spaces, at least for set names. Okay, but sometimes we have some issues with spaces, so I don't really like to use it at all because I want to avoid these issues at all cost. Click on OK. And now we should define a new tie node set. And we should select this other node to be part of this tie node set. I'm going to teach you one, well, it's going to be a little confusing, but you're going to get used, okay? So I'm going to teach you one way we can do this. Select this field, question mark, to open a list of options. We don't have yet a set for it, so we should create. So right click, new. Now we should select here set. Okay, so if in your case it's selected connector in this, then we are going to be able only to select connectors for the set. But we want to select a node, so you should select node and then select this node here, because for the tie node set of ARM2 we selected this node. So for this other rigid body we should select this node, this one right here. Middle mouse button. Now we should name this, I have in my Control V the name of the rigid body, and I'm going to put underline tie node, tie nodes. And in the output type, I'm going to say that this is a node set. Sometimes we don't really need to define that this is a node set because Abaqus will recognize it automatically, because it's going to see that this set is composed of only nodes, and then it's going to be recognized as a node set. But I like to define it most of the time. Click on OK, and then double click in this new set that we just created, and you see that now we have the ID of this set here in this rigid body. Click on OK, and you see that double click on rigid body, select this rigid body, and let's zoom in here, and you see that there is a line coming from this point that we defined as the tie node set that is now attached to this rigid body. Okay, so that's the meaning of a tie node. It becomes part of the rigid body that that we defined this tie node set for. Okay, now these two rigid bodies are connected by this hinge. And the last thing I want to do is to make the position of these two nodes coincide. And to do this, I'm going to use the match function, which matches the position of two selected nodes. It's in the deck module, but we have this function also in the mesh module. Okay, let me show you. Click here and hold, and then select classic mesh. And then here in grids, click here to show more options. And then we have the match function here. Click and hold, and then select manual. Select the node that you want to move, which is this one, and select the node that you want it to be moved, which is this one. Middle mouse button. Okay, in that way, we are going to have two nodes in the same X, Y, and Z position. Double click on nodes, create a box selection, maximize the column that shows the ID, and you see that we have two nodes in the same position, which is okay, we can have it. Okay, one node is related to the tie node set that is related to one rigid body, and the other node is related to a tie node set that is related to the other rigid body. Okay. Okay. Now let's activate the visualization of rigid, and we have finished this connection. Now we can create another rigid body. So let's now activate the visualization of CAD. The next one I want is let's use this tool again to isolate by PID. Select this part and middle mouse button. It is this part. Well, maybe let me show all again. Okay, maybe for visualization purposes, I'm going to also get this tube. So again, using this tool, selection filter PID, select this part and this tube. So it's going to look better. Okay. All right. Now let's go through that same procedure. I'm going to be much faster now. In the classic mesh, use length to select everything. Middle mouse button, length is 20, press OK. And before we continue, file, save. So if something goes wrong, we are going to have a backup. Now let's use the free algorithm. Select everything, middle mouse button, and now we have a pretty bad mesh. And it's getting even, distorted here. Well, this is kind of bothering me a little, but that's okay. It's not so beautiful. Well, yeah, that's okay. I'm not going to waste time adjusting it. If it was a real project, I would not let it like this because it's distorting too much, If I would have to present it, having not good quality elements like this is okay if it's not distorting the geometry, because when I get to present it, I'm not going to let the mesh visible. I'm going to let just the format of the mesh, but not the lines of the mesh. But in this case, even the format of the mesh is not going to be beautiful. Okay, but that's okay. Let's not waste time with it, because the purpose of this video is not to show how to deal with meshes yet. The next step is to go to volume mesh, release, select everything, middle mouse button, deactivate the visualization of macros. Now we see only elements. Go to Abaqus deck. Let's use the utilities function inside the element group, change type to the entities. From shell to R3D, select everything, middle mouse button, close this, double click on rigid body. We have this additional rigid body created. The reference node is here on this COG. Double click on it. I'm going to say that this is connecting. connecting mechanism 2. Control C. Let's go to the element set that was created automatically. F2. Control V. Okay. And let me point out one thing. F2 here in the element set. Well, this is an element set, and usually I like to output as element set. But for rigid bodies, I don't like to do this, and we are not going to face any issues because when we input it in Abaqus, it's going to be recognized as an element set automatically. I don't like to define it as an element set because of, well, when I want to filter the sets that we have, and then when I want to filter the element sets, I don't want the element sets related to rigid bodies to appear. Okay, this is something that you're going to understand in the future. Maybe not in this module, because in this module we are not going to have element sets that are not composed of rigid bodies. Okay, so this is just a practice that I like to do or to use, but if you want, you can define here as element set. Okay, it's okay. Now, click on OK. And let's show all. We should connect this new rigid body to the previous one that we created, again using a hinge connector. So let's do it faster now. Go to topo module. Let me deactivate my camera. In here, let's create a point on COG circle. Select 3 points here. And also on the other side. COG points. Select this point and this one, middle mouse button, and a third point is created here. Deactivate the visualization of rigid. Go to Abaqus deck. Let me activate the camera. Now let's create a new rectangular coordinate system by clicking here, rectangular. This is the origin. This one is to define the z-axis direction, middle mouse button. We know that we should generate a rotation about y of -90 so that we are going to have the x-axis in this direction. Click on OK. Now we can create the hinge connector. In the deck Abaqus, click here inside the elements group, this button. Click and hold, select 2 nodes. Select this one, and then this one as the second node, middle mouse button. Select the connectors part. And then you see that it has chosen a PID automatically, and this is dangerous because we don't want to select an existing PID for this connector. To change it, we should select this PID question mark to list the options that we have. We have these 2 options, and I want to create a third option. Right click, new, and Control V, because I have the name of this. Actually, this is connecting mechanism 1 to 2, right? It's connecting the connecting mechanism 1 and 2. This is a hinge. Search for a hinge, and the orientation of node 1 question mark, and this should be this coordinate system with ID 3. Middle mouse button, and then click on OK. Now we are going to select this new PID that we have created. Double click. Now we have the ID of this PID. Click on OK. And now this is correct. Close this. And now we have this new hinge created. Okay. Now let's activate the visualization of rigid, and one of these nodes should be related to a tiny node set of this rigid body that we had created previously. So let's do this. Double click on rigid body. For this rigid body, double click on it. There is this tiny node set with ID 6. Control C on this ID, close. Let's go to sets. Control V here in the searching filter, press enter, and then here we have the set. Right click, modify contents. And then we can select this node or this node. Let me deactivate the visualization of rigid here. And then you see that right now we have only one node in this set. And I'm going to select this node, for example. And then you see that we have now two nodes for this set. Middle mouse button. And let's confirm. Yes, we have two nodes. Okay. Close. One node is up here in this other hinge. Okay. Now we should create another set. So right click, new. We should select node here and then select this other node. Middle mouse button. And then the name is, well, hopefully I have it in my Control V. No, I don't. But I guess this is connecting mechanism to tie node. This is a node set. Let's copy the ID of this node. Control C, which is 8. Click on OK. Close this. And double click on rigid body. Let's go to this rigid body. And let's Control V the ID of that set that we have just created, which is 8. If you didn't Control C that ID, you can click here on this field, question mark, and then select this set by clicking here. Click on OK. And the last step is to match the position of these two nodes in a way that we are going to have both nodes here on the COG. To do this in the exact module, in the Abaqus module, inside the node group, there is this function match. Click and hold manual. Select this node and then this node. Middle mouse button. Now we have the two nodes in the same position. Now let's activate the visualization of rigid. And we have these two rigid bodies connected. Now let's we should now create another rigid body. Let's do this. Let's activate the visualization of CAD. Let me think here. What is the next one? Well, the last one is the one that has everything that is left here. Okay, so there is just one left for this mechanism, and then we can try to run it. Okay, and then later we are going to model these hydraulic actuators. Let's not do this right now. We are going to do this later. And also there are some rigid bodies that are going to be here. Okay. And the cool thing is that we have a connection between two gears here, and we're going to use something very interesting that is related to equations here in Abaqus. Okay. Okay, so let's use this tool to isolate some parts, this one. And select here PID in the selection filter. Let's select this PID, this one, this one, this one, this one. I guess that's all we need. Middle mouse button. Let's use this function here, invert. So it's going to show the inverse, the parts that was hidden. I'm confused if I should include this tube. To include this tube, press ESC. Actually, select this function, not. Select this tube, and now it's hidden. And now we can click here in invert. And now we see everything that was not visible. Oh, okay, I guess we should include this tube as well. Now let's go to the classic mesh module, length, select everything, middle mouse button, 20. Let's use the free algorithm, selects everything, middle mouse button. Let's go to volume mesh, release, select everything, middle mouse button, deactivate the visualization of CAD. Now we see only elements. And let's go to the Abaqus deck, utilities, change type 2D entities. From shell to R3D, select everything, middle mouse button, close this. Double click here in rigid body. We have this new rigid body. And to be honest, I don't really know what's the name of this part of the excavator arm. I don't really know how to name these. There must be a technical name for this. This is to pick things from the ground. Pick tool, maybe. Probably this is not the most appropriate name, but that's okay. So we have a reference node that was created on the COG automatically. We have an element set, Control C, this name, F2 here, Control V, and underline rigid elements. Click on OK. Click on OK. Now this one is going to be very interesting. Let's click in Show All. And this one is going to be very interesting because we are going to have this rigid body connected here and also here using two hinges. Okay, okay, let's do this one first. Go to Topo Module. Let me deactivate the camera. Points on COG, circle. This circle right here, select 3 points that are part of the circle, rotate the view, do the same thing here. Now point on COG of points, select this point, and then this point, middle mouse button, deactivate the visualization of rigid. You see that we have these 3 points. Don't zoom out because you're going to get confused because there are other points here. Okay, let's keep these 3 points in our view. Go to the Abaqus deck, coordinate rectangular, select this one as the origin, this one to define the z-axis, middle mouse button, rotation axis 2, -90, press OK. Now let's create the hinge connector 2 nodes. From this one to this one. And you see that, well, there is one thing that is interesting here. In the option list, you see that the property is going to be the current. Well, current means the last one that we had used. And I don't want this to happen. I don't want this hinge to have the same property that we had used previously. I want to create a new one. So let's change it to ask always. Middle mouse button, select this part that we had created for all connectors, double click on it. And then there is a list of properties that we can select. I'm going to, so when I chose here to ask always, this is what it means. It's going to ask what is the property that we want to use for this connector every time we create a connector. Okay, Let me activate the camera. So let's create a new one. Remember that we should use different properties for each hinge, because each hinge is going to have a different coordinate system. Right click, new. The name of this one is going to be peak 2 to, I don't know what is this other rigid body. Maybe this is the connecting mechanism 2, maybe. We can check it later. Okay, this name is just for organization. You can give any name you want, okay? And you can even you don't need to give it a name, okay? It's not an obligation. This should be a hinge, and select here question mark and select this coordinate system that we had created that has ID 4, double click, and then press OK. And then this is the new property that we had created, so double click on it, and here we have the ID for this property, node 1, node 2, and the ID of the connector. Click on OK, close this. Now let's just let's activate the visualization of rigid. We are creating this hinge. Oh, actually this one is going to be connected to the arm 2. So double click here in peak tool. Actually, sorry, double click on connector. Select this connector that we have just created. So we have it selected here, double click on it. In the PID, select it and press F2. And let's rename it as peak tool to arm 2, which is the other rigid body that we want to connect. That's how I like to organize the name of hinges. Okay, I just put the name of the 2 rigid bodies that I want to connect. Press OK and press OK. Now we should define the tie node sets. We already have a tie node set for the arm 2. So double click on rigid body, select arm 2, double click on it. There is this tie node set with ID 4. Control C this ID, close this. Now let's go to sets, search for 4, press enter, select this one. And then you see that we have already 2 nodes for this tie node set. Now we are going to include another node, and we are going to have a total of 3 nodes. Right click, modify content. We have 2 nodes. Deactivate the visualization of rigid and select this node here, for example, this one. Now we have 3 nodes. Middle mouse button, confirm that you have 3 nodes. Now let's close this. And now we should create one new set to be the tie node set of this new rigid body that we had just created, which is the peak tool. So go to sets, right click, new, select node here so that we are going to be able to select nodes in the viewport, and select this node here because this one was selected for the other rigid body. So this one should be selected for this rigid body, this one. Middle mouse button. This is a node set and the name is peak tool tie nodes. Oh. Let's copy the ID, which is 10, Control C. Press OK. It is 10 in my case. In your case, it can be a different ID. Close this. Double click on rigid body. Double click on peak tool. And then in the tie node set, Control V that ID. Or you can press question mark and select the node set here. Double click. Press OK. And the last step is to match the position of these 2 nodes. So let's use the match function, manual, select this and then select this middle mouse button, and then this rigid body is connected. Now let's activate the visualization of rigid. Let's see. Yeah, we have this. And to end this video, let's create this other rigid body and let's maybe try to run it. Okay. Okay, let's be fast. Topo module. Let me deactivate the camera. COG of circle. This one, and this one. Middle mouse button. Rotate the view. 3 points here. COG of points. This one. Middle mouse button. We have a point right in the center. Deactivate the visualization of rigid. Now let's go to the Abaqus deck. Coordinate system, rectangular. This point and this point. Middle mouse button, rotation about Y, minus 90 degrees. Press OK. Now let's create the hinge to nodes from this to this. Middle mouse button. Connectors part. Right click, new. And then we're going to set this name later, but I guess it's peak 2 to maybe connecting mechanism 2, maybe. Select hinge, question mark in the orientation, select this coordinate system with ID 5, double click, press OK, select this new PID created for this one, which is here. Press OK. Close. Activate the visualization of rigid. And let me check if this rigid body is the connecting mechanism 2. Double click on rigid. Connecting mechanism 2. Yeah, that's correct. Well, we have a tie node set for both rigid bodies, so I just need to modify it. Deactivate the visualization of rigid. Let's zoom in here in this hinge. Let's go to sets. Click here in this X to clear the filters. Let's get the peak 2 tie node set that has only one node. Right click, modify content. And let's add this node to this set, this one here. Now you see that we have 2 nodes, middle mouse button. And we should also modify the connecting mechanism to tie node. This one, right click, modify content, and select this other node. Okay, be careful here. This other node, because this one was selected for the other rigid body. Middle mouse button, and now we have 2 nodes for this set. Okay, now let's use the match function in the Abaqus deck group node group match manual. From here to here, middle mouse button, and we are finished. Let's activate the visualization of rigid. Now we have everything connected, but I don't think this is going to work because the hinge connector creates over constraints if everything is not perfectly aligned. If there is a little of disalignment between the x-axis of these hinge connectors, then we are going to face an issue. And this disalignment can be caused because of the CAD, okay? Because the CAD may not be so perfect. And remember that we had defined the axis direction by using these points that we created on the COG of each circle. Okay, let's try to run this test. And if it doesn't work, we are going to transform these connectors into Cartesian coordinates, but we are going to do this in the next video because this video is too long already. Double click in step manager that is inside the step group. Double click here. Now let's maximize this. The step manager is really important because it has all the steps of this analysis. Oh, let me teach you how to do this. To translate the view, you should hold the Control button and use the middle mouse button. Okay. The left mouse button rotates, middle mouse button translates, and the left mouse button rotates like this. Okay, so we have only one step. Let's maximize to see what we have here. And let's maximize the type column. We have a connector motion created for this hinge. We can keep this connector motion, that's okay. And we have this boundary. Double click on it and select this. Well, for this boundary, we are fixing the reference node of the arm1 rigid body. Okay, we are going to keep this rigid body fixed. Now let me think here what we can do. We can create an additional coordinate system to rotate this hinge, because then we are going to have this rigid body rotating. And in that way, if we have it rotating, it's going to make this the peak tool to move in a certain manner. It's going to open the peak tool. Well, I guess this is going to work. Let's test it out. In the connector motion, well, we are going to create one additional connector motion. Close this. And in the deck Abaqus, go to boundaries. And then you see that we have this button here, connector motion. If you're not able to see this, you should click here to see more options and see if it's hidden here. In my case, it's here. Click and hold, select element, zoom in and select this hinge connector here. Middle mouse button. And then we are going to create this rotation in the first step that we had created before. And this is going to be a rotation about 4, which is rotation about the local x-axis. And we can rotate it by 0.5 radians, which is approximately 30 degrees. Okay. So let me explain one additional thing that is very important. How do we know what is the direction that this is going to rotate? Well, we should use the right hand rule, with the direction of the local x-axis. Okay. Well, let me try to explain this. Let me click here on OK to create this connector motion. Double click in connector motion. You see that now we have this new connector motion created, right? Let's double click on this connector motion that we had created previously, which is this one. Double click on it. Let's copy this rotation. Copy. Press OK. And double click on this one that we have created just now, and let's paste it here. Okay. So we are going to have the rotation equal to 30 degrees exactly. Click on OK. Now let's do one thing here. Double click on connectors. Select this one that we had applied this connector motion now. And then you see that we have it selected here. Right click and show only. Now we have only this connector. Zoom in until you see the coordinate system of this connector. And you see that the x-axis is like this. It is to the right. You should position your thumb, your right thumb, along the x-axis, and the positive rotation direction is in this direction when you rotate your hand like this. This is how you know what is the positive direction of rotation of a hinge. In this case, I actually want to create a negative rotation about x because I want to open this arm. Let me see. Let's show all by clicking here. Zoom out. Let me see. I want to rotate it in the... Well, if we look at it like this, the x-axis is to the right. I want to rotate it in the counterclockwise direction so that this arm is going to open, hopefully. Counterclockwise direction. And by using the right hand rule, the positive direction is in the clockwise direction, so counterclockwise direction is going to be negative. Okay? So in this, let's go back here to connector motion. select this one, double click, and let's put a negative sign here. Negative sign. Press OK. Okay, let's see if this is going to work. Let's run this. I'm going to open the working folder that I had created for this. Let's go back here to this one, create a new folder. And I'm going to name this as test 2. Okay, let's open this folder. Let's copy the path to this folder. And before we output this, I'm going to click here, compress. So it's going to delete all unused entities. So we are not going to have any issues in the output. To delete everything, select here all decks. Because, well, we have many decks here for many solvers, and maybe there is one entity from another deck that's not appearing here, and that I don't want to be in our model. Okay, this is just to clean this model. We can click on details to show what's being deleted. Deactivate everything here and activate again, because in that way we are going to have everything activated. Scroll down and looks like there is nothing that is going to be deleted. So this model is already clean. Maximize geometry, there is nothing here. Maximize groups, there is nothing here. Okay, we can press OK, but nothing to compress. There is nothing to compress. Well, now let's click on File, Output, Abaqus. And double click here, erase, and Control V, because I have the path to that folder that we had created here. Press Enter. Now we are in that path. Let's name this as test_2.inp. INP is the extension of the input file for Abaqus. This is the file that we input there. Save it. And then here we have this issue with the size of my screen, which is small. We can reduce the lateral size by doing this, and you see that the height is automatically adjusted. Now we can reduce the height like this. And then the version could be 2022. In my case, the version of my Abaqus is 2022, and output all. And in comments, we can select none, because I don't want to have any type of comment. Click on OK, and then you see output completed. Let's go to this folder. Double click on this. Well, you can open this input file using Notepad++ or Notepad. And here we have the definition of the whole module. We have the definition of the nodes. Control F, search for asterisk element. We have the definition of the elements, connectors. So you see how is the definition of a connector. This is the command used. Let's see, we have the connectors, and here we have the definition of the rigid elements. And down there we have the definition of the steps. Okay, here we have the definition of these steps. In the end of this analysis, when we have everything ready, I'm going to go through the input file to explain everything to you. Okay, I don't want to do this right now. Let's do this at the end of this tutorial. Now to run this, we are going to do this in a different manner. We are not going to open up Abaqus CAE application. We don't need to do this. We did it in the previous way that we ran the first test. But now we are going to run it using cmd command. To do this, you should right click on this folder, and there is this option open in terminal. If in your case you don't have this option, you can go to window and search for cmd, command prompt. Open it, and then you see that we are in this folder, and I'm going to copy the path to this folder again, Control C, and then I'm going to paste it here. Before we are going to click cd space. cd is the command to go to a specific folder. And then here we can paste the path to that folder, Control V. And then here we have the path to that folder. Press enter, and now we are in that folder where we have this INP file. To run this analysis using Abaqus is very simple. We should simply type Abaqus space job equals. And the name of the job should be, well, I closed that folder. Let me go back here. The name of the job should be the same name as the input file. So I'm going to copy this name, test2, without the .inp extension. Let's go back to the command prompt, and then I'm going to paste it here. So job equals test2, and then we can put some other arguments such as how many CPUs I want to use to run it. But well, I'm not good. Well, we can do this. I'm going to space and CPUs equals 2, for example. I have 8 threads in this computer. I can run with up until 8 threads, but since this is a pretty small module, I can run it only using 2 threads, 2 nucleus. Press enter. And then when we do this, the job is going to be created with this input file, and it's going to be, well, it's going to be run in Abaqus. So Abaqus is going to solve this. So you see that we don't need to open Abaqus CAE and import the input file there, create the job and submit it. We don't need to do this. Daily, I don't even use Abaqus CAE application. Okay, I use only ANSA, and then I run in Abaqus using command prompt. And this is what most people that work in this industry does. They use a preprocessor software to create the module, and they use the solver itself just to run the module. At least for Abaqus, this is how it works. For softwares like ANSYS, there are people that work in the using the ANSYS applications, but there are also people that create the modules using ANSA and ANSYS deck. Okay. Well, we have these files generated. Let's see. Well, probably we have some issue here. And to see what is this issue, we can check the .dat file that was generated. Right click and open with Notepad++, or not Notepad. And let's search for Ctrl F, and let's search for asterisk error. Press enter. Oh, okay. So it's not recognizing a material, probably because, let's go back here to ANSA. Let's click here in materials, and you see that there is this material here that is not defined. You see that we have it not defined. Let's see where this material is used. Right click and click on reference, and this is being used by many shell sections that are related to the CAD. I don't really want to export CAD entities, but well, to solve this issue, let's just click on defined. And now that we have this material defined, let's copy the path to this folder, and let's click on File, Output, Abaqus, and then you see that we are already in that folder. You see that we have the input file that we had created previously. Now select this input file, just click once so that we are going to have this same name defined here, and then click and save, and then OK, and then click on OK to overwrite that file. Okay, now we have the input file updated. Let's delete everything but the input file. Delete. Okay, we have this input file created. Now we have that material defined. It's not going to be used for the rigid body, so it's not going to make any difference in the results, but at least it's not going to generate that problem. Let's open the command prompt again, and I'm going to use the up key keyword to get the previous text that we had written, and then I'm going to press enter. Okay, so in that way I'm putting this to run again. Let's see if this is going to run. Okay, now it's going to run. It's generating the files. The .sta file is the one that contains the one that we can use to see the increments and everything else. It finished running. Let's open the .sta file using Notepad++, and you see that it didn't run. We had 5 cutbacks in a row, and the reason for that is because this module is over-constrained. Well, for that reason, we should use Cartesian cadence instead of hinges, and it's going to be pretty easy to perform this modification, as you're going to see in the... Well, let's see if we have some more time here to do this. This video is 1 hour and 16 minutes long. This is too long, and I don't want to do it in a hurry. I want to explain about Cartesian cadence for you, which is the type of connector that we are going to use. And in the next video, we are going to fix this issue, and we are going to continue creating the other rigid bodies, because we have some other rigid bodies here, at least 2 additional rigid bodies here. And we also need to model the hydraulic actuators. Okay, so in the next video, we are going to finish this tutorial, and we are going to have this mechanism completely simulated. And well, by doing this, you're going to learn a lot about rigid bodies and connectors. And this is really important. And I'm going to show why this is important with one example in the next video, which is the cross-cart example. Okay? But in a nutshell, this is important, for example, when you want to simulate a vehicle, a full vehicle going through events such as it going through a bump or hitting a trench or things like that. And when you do this, you should, well, it's not that you should, but you can model the whole vehicle as many rigid bodies connected by connectors. This is one way you can do this. I'm going to talk more about it in the next video, okay? Oh, I guess I don't have the camera activated. Okay, so that's all I had for this video. In the next video, we're going to continue and we're going to finish this module, okay? I hope you are liking it. I hope you are learning many things with this tutorial, and see you in the next video.